All right, hello and good morning. My name is Travis Heine, and today I will be speaking about a fascinating topic that I am very passionate about. Ways that we are facilitating the transition from electricity being generated with fossil fuels to being generated with the energies of the future, i.e. renewables and nuclear. An exciting way that we are doing this involves a technology called GIS, or Geographic Information Systems. I will explain more about GIS in this presentation, but if you're not already familiar with it, just know that it is a mapping tool on your computer that can tell you all sorts of information about any location on Earth, for example, its altitude, slope, or proximity to other locations. This is all valuable data that informs decision makers and planners who are looking for the best place to locate whatever it is they want to build to generate electricity, wind turbines, solar panels, or nuclear power plants. But it's not perfect information, and it is limited by the availability and the type of data that is accessible. The transition away from fossil fuels is a formidable challenge. It demands near perfect information to effectively plan, some of which we don't have. Still, there are improvements that can be made to existing tools, one of which is the topic of my thesis and what I will be showing you very soon. But a big part of my presentation this morning will be to emphasize the importance of this area of research. When I said I'd be showing you the improvement very soon, I meant it. So when I gave a practice presentation in class, it was suggested that I give to you all a sneak peek of these pictures so that you can all understand the simplicity of the improvement I made before I explain why it matters and the complexity of why it matters. And so in the picture on the left, you can see that the proximity between the AES Petersburg power plant and the transmission lines is what is measured. This is the quote data. My simple improvement is, in addition to measuring the proximity, to measure the capacity of that proximate transition. This has significant implications for investors that will become more apparent as I continue. Because my thesis and the GIS tools that I will be talking about involves, because the thesis and the GIS tools that I will be talking about involve setting nuclear power plants, please allow me to share some amazing facts about this power source that help to highlight the salient role that these GIS planning tools play in assisting its successful deployment. Unfortunately, I can't spend as long as I'd like to talking about nuclear power, and I'll have to run through these next couple slides somewhat quickly. But let's look at what are 4 important properties to consider for any energy source: safety, environmental impact, utility, and cost. So, safety first. Measured as deaths per terawatt hour of electricity production, this graph shows the death rates from accidents and air pollution that result from various energy sources, including fossil fuels like coal and oil, and renewables such as solar and wind. Again, this does not measure absolute deaths, but rather this graph is a measure of death rate relative to the amount of electricity that energy source produces. So here, nuclear power ranks the second safest, just behind solar. So we're going to give nuclear a check for safety. Next, environmental impact, measured in emissions of CO equivalents of electricity over the life cycle of a power plant. Nuclear power plant ranks the lowest. No surprise here, as nuclear power produces no emissions. But even considering the mining of uranium ore, nuclear power still ranks as the lowest life cycle emitter. There is no time to get into radioactive waste this morning, but let's just say there's surprisingly little of it. We're going to give nuclear a check for environmental impact. Here's where nuclear really shines, providing lots of reliable power. This graphic from the DOE explains that it takes 3 million of the average solar panel to equal 1 average nuclear reactor, which is a lot. But this graphic doesn't account for the capacity factor of these 2 power sources. Capacity factor is the ratio of a power plant's actual output over a period of time to its maximum possible output if it ran at full capacity continuously during that same period of time. Nuclear power plants almost always operate at maximum output. Solar panels cannot. With capacity factor included, it takes almost 12 million solar panels to equal 1 nuclear reactor, which is really staggering. So for utility, we're going to give nuclear a check plus. And then cost. So finally, cost. Cost is where nuclear power begins to look a little less desirable to investors. I don't really have time to explain exactly how this graph is calculated, but check out David Ruzek, also known as Illinois Energy Prof, on YouTube. He uses real-world numbers to show how even through nuclear power, he uses real-world numbers to show that even though nuclear power involves massive investment, it will eventually have a higher return on investment than natural gas power plants. That is what this graph shows, with nuclear in blue and natural gas in red. And when I say it will eventually outcompete a natural gas plant, I mean in 3 decades. And during the construction of the nuclear power plant, the numbers will go billions of dollars into the red. It's definitely not a project to be taken lightly, and this really highlights the importance of planning tools like GIS for nuclear power plant siting. Okay, so Geographic Information Systems, more commonly known as GIS. If you haven't heard of GIS before, then think of it like stacking transparent sheets on top of a map. One sheet might show rivers, another roads, another population density, and another where power plants are located. When you stack them together, you can see how all those things interact in one place. GIS doesn't just store pictures of maps. It connects data like this county has 50,000 people or this land is prone to flooding to exact locations. Once you've got the layers, GIS lets you ask questions like where's the safest place to build a school or which areas are most suitable for a nuclear power plant. It crunches the data and highlights the best spots based on the rules you set. And this leads to how those rules are set. Multi-criteria decision analysis, or MCDA. This is called MCDM on my slide, but they mean the same thing. And this is an algorithm that the GIS analyst model will obey. Think of it like making a decision with a checklist. Imagine you're trying to figure out the best place to build a nuclear power plant. You wouldn't just care about one thing, like local energy prices. You'd also care about flood zones, access to cooling water, how much the community supports it, or access to transmission lines. MCDA, or MCDM, is the process of lining up all of those criteria, deciding how important each one is, and then running the algorithm to produce an overall score based on those criteria. In practice, the better the MCDA, the more safe investors will feel that a reliable site has been selected. These are the two premier GIS tools that exist for siting nuclear power plants. Both were developed by the US Department of Energy. The first, OR-SAGE, is a research visualization platform developed by Oak Ridge National Laboratory that utilizes over 60 data sets, focusing on safety and technical considerations. These are considerations such as slope, seismic zones, floodplains, proximity to hazardous facilities, and much more. It uses a rules-based exclusion and suitability criteria to produce maps of candidate areas, and the tool also supports scenario analysis about how different policy or technology choices change siting outcomes. The second tool, STAND, which stands for Siting Tool for Advanced Nuclear Development, is a practical, stakeholder-oriented web tool developed to help industry, regulators, and communities answer, quote, where and why for advanced nuclear deployment. It organizes variables into three primary domains: socioeconomic, proximity, and safety, and provides county-level reports, regulatory context, and comparative analyses across candidate sites. The STAND tool notably includes a county-level public sentiment measure toward nuclear power as a part of its socioeconomic data that was collected by the National Institute for Risk and Resilience at the University of Oklahoma in a decades-long study. Okay, so here we can see inside the STAND tool, we are looking at a measure called transmission lines. But what does this measure? According to the STAND tool, the definition of this measure is, quote, the distance from site in miles to the nearest point along an electric transmission line. And yes, this is what I showed you in the sneak peek at the beginning of my presentation with the proximity to the transmission lines. On the right side of the slide, you can see some different candidate sites that are being compared using this measure, and this is just to illustrate the simplicity of the data. It just gives you a distance in miles. So for my study, I borrowed a list of potential sites for coal to nuclear retrofits that was assembled by Mohammed R. Abdusami et al., who in their study systematically evaluated all sites using the STAND tool, arriving at an overall score for each candidate site, which you can see here as the functional value. I then isolated the Indiana candidate sites. Notably, Abdusami et al. Divided candidate sites into two groups, and their findings revealed the top candidate sites nationwide in both groups as being located in Indiana: R.M. Schaefer in Wheatfield, Indiana, and AES Petersburg in Petersburg, Indiana. So now that I had my list of Indiana coal to nuclear retrofit candidate sites, using ArcGIS Pro, I layered the data from the Abdusami study along with a map of US transmission lines. I found that I could see where the transmission lines connected to the substation of the coal power plant, which I then verified in Google Maps satellite view. I used this as my threshold. Rather than a radius from a power plant, I only selected transmission lines that connected directly into the power plant's substations. hopefully this picture makes more sense now. I definitely need to add in here that this particular level of detail of proximity versus capacity is not a small difference for potential investors. Limited grid capacity is already a bottleneck for new power sources coming onto the grid, and the fees that generators need to pay to access the grid, called interconnection fees, are in the tens of millions of dollars. These fees will increase when transmission load increases or capacity is not as high. So the STAND tool itself points out that in the 2008 American Electric Power Fact Book, it states that high voltage above ground power lines can cost in excess of $1 million per mile. So just further illustrating that getting to extra transmission capacity can be prohibitively expensive quickly. All right, here are my findings when so finally I can show the results. As you can see, Clifty Creek Power Plant, which ranked last of all Indiana coal power plants according to the STAND Tools score that the Abdusami study gave it, the Clifty Creek Power Plant was last, and it has the top capacity. So this indicates that measuring capacity could significantly alter the overall favorability scores that are generated by STAND. So for future considerations, if OR Sage or STAND were to integrate this layer of analysis into their tool, I would recommend that they find better transmission data than the data set that I used in this study. The transmission data I used included line voltage, but the data lacked other technical specifications that influence capacity, and more importantly, they do not include the active load on the lines.